So, have you ever really stopped to think about what it takes to build an intelligent robot? I'm not talking about a simple machine that just follows a pre-written script. I mean a robot that can actually see, think, and interact with our world. What are all the pieces you need to put together, from the physical body right down to the AI that makes it tick?
All right, let's get into it. Here's the game plan. First, we're going to give our AI a physical body. Then, we'll build out its nervous system and, of course, its brain. After that, we'll tackle the huge challenge of getting it out of a computer simulation and into the real world. And finally, we'll take a look at what our future with these incredible machines might actually look like.
Okay, first things first. The biggest leap for AI right now is moving out of the digital world, the world of pure data, and into our physical one. This isn't just about writing clever code anymore. It's about giving that code a body. And you know, this difference is absolutely crucial. On one hand, you've got your standard digital AI. It's fantastic at crunching through data that's already been prepared for it, like sorting through a million JPEGs of cats. But on the other hand, you have embodied AI. This kind of AI has to learn through direct, messy, real-time interaction with the world around it. One knows the concept of a cat, the other one learns pretty quickly what happens when it tries to pet one and gets scratched. And when it comes to building that body, we're seeing two totally different philosophies play out. Look at Tesla's Optimus. It's being designed from the ground up for mass production. It uses electric motors that are cost-effective, and it's built to leverage all the AI tech from their cars. Then you've got Boston Dynamics' Atlas. This thing is a beast. It's a high-performance research machine, using super powerful hydraulics to pull off these mind-blowing feats of agility. See? Two very different goals, leading to two very different robots.
So, we've got a body. What's next? Well, a body is pretty useless if it doesn't have a nervous system to control everything. How do you actually connect all the different parts, the sensors, the motors, the processors, so they work together as one?
Well, right at the heart of the robot, you need something like a brainstem. It has to be a small but incredibly powerful and efficient computer that can handle all those low-level, real-time jobs. The NVIDIA Jetson Orin is a perfect example of this. It's basically a tiny supercomputer, and it's designed to process the absolute fire hose of data that's pouring in from cameras, lasers, and all the other sensors at the same time.
And to get all those parts talking to each other, we need a central nervous system. In the world of robotics, that's something called ROS2, which stands for Robot Operating System. Think of it as the universal translator and the main switchboard for the robot. It's the software that lets the eyes, the hands, and the brain all communicate with each other reliably and instantly.
So here's how that flow actually works. Let's say a camera, the robot's eye, sees something. That image data gets published onto the ROS2 network. The AI brain is listening, it grabs that data, figures out what it's looking at, and decides what to do. Then it publishes a new command, something simple like move arm to this position, and the motor controller picks up that command and makes it happen. It's just this constant, super fast loop of information. Okay, so our robot has a body, check. It has a nervous system, check. But how does it actually, think? How does it go from just seeing pixels to understanding what it needs to do and then making decisions? This is where we get to the cognitive layer.
And this brings up a really important question. How do we actually tell the robot what we want? Do we have to sit down and write lines and lines of complicated code for every single little task?
Amazingly, the answer is no. Thanks to the power of large language models, LLMs, we can now just talk to it in plain English. The LLM acts like the robot's prefrontal cortex. It's the high-level planner that can take our abstract goals and translate them into concrete actions the robot can understand. The way the LLM does this is through a process that researchers call chain of thought. So, if you give it a big vague command like clean the kitchen, it doesn't just freeze up. Instead, it logically breaks that goal down into a series of smaller, doable steps. Step 1, find the sponge. Step 2, go to the counter. Step 3, wipe the counter. It creates a simple, step-by-step plan that the robot's other systems can actually follow. All right, now we come to what is arguably the single biggest challenge in all of robotics. It's one thing to train an AI model to work perfectly inside a nice, clean, predictable computer simulation. But how on earth do you make sure it's not going to fall flat on its face in our messy, chaotic, and totally unpredictable real world? This problem actually has a name. It's called the reality gap. And it's all about the million tiny differences between the simulated world and the real one.
Things you'd never think about, like the exact friction of a floor, or the static and noise in a camera's sensor, or the tiny little delay in a motor's response. A simulation can get close, but it can't capture these perfectly, and any one of them can cause a perfectly trained robot to fail instantly.
So, how do we get across this gap? The solution is a really clever technique called domain randomization. The idea is, instead of trying to train the AI in one single perfect simulation, you train it in millions of slightly different ones. You're constantly changing things: the lighting, the color of objects, the friction, the physics. You basically randomize everything that could possibly be different in the real world.
And this approach has led to some absolutely mind-blowing results. Just look at OpenAI's Dactyl project. They trained a robotic hand to solve a Rubik's Cube. But here's the kicker: the AI was trained entirely inside a randomized simulation. The very first time the physical robot hand touched a real cube, it already knew what to do. It was ready for the chaos of reality because it had already seen a million different versions of it.
So, we've built our robot, we've given it a body, a nervous system, a brain, and we've even managed to bridge that tricky gap to reality. So now let's zoom out a bit and think about what happens when these machines finally step out of the lab and into our everyday lives.
As we head down this road, there are some massive questions we really have to start thinking about. The economic shift from humanoid labor is going to be huge. It'll reshape whole industries and the job market as we know it. And right alongside that, we absolutely have to develop strong safety frameworks to make sure these machines operate reliably and predictably around us.
And don't think this is some far-off future. The timeline is accelerating like crazy. Projections are showing a massive ramp-up in what these robots can do and how many there will be. Some experts are even predicting a future with billions of autonomous robots integrated into our society and economy by the end of this decade.
So when you boil it all down, it really comes to this. We are, right now, actively designing and building the intelligent physical machines that are going to work beside us, live in our homes, and become a fundamental part of our world. The real question is, as we're getting them ready for us, are we getting ourselves and our society ready for them?